Okay, in 3B, we're looking at scientific notation and using that in problems and in calculations. So scientific notation is basically a way we can deal with really large numbers and really, really small numbers by just focusing on the first few non-zero digits of a number. And then we just use a times 10 to some power just to say what place value those numbers go in. So, for example, the distance from the Earth to the Sun is 149,600,000 kilometers. The number is so big, it's usually listed in scientific notation, which is 1.496 times 10 to the eighth. So, some common powers of 10 that we see are million. And so, million is a 1 followed by 6 zeros, which means million is going to be 10 to the sixth power. Billion, you're just adding on 3 more, so it's 10 to the ninth power. And trillion is 1 more set of zeros, so that is 10 to the 12th power. Okay, so there are rules for scientific notation. The rule is that this first number has to be a value between 0 and 10, or between 1 and 10, sorry. You can't have the first number has to be something that's not 0. So if it was less than 1, it would be 0 point something, and we don't like that. So it's got to be some number followed by your decimals. Okay, and then k is going to be the power of 10. That tells us how many times you need to move your decimal point in order to get to the right place value. Like I said, it's the because our place values are powers of 10, it just tells you how many times to move the decimal to get to the actual number you're thinking about. So if you have a number that's bigger than 10, or bigger, sorry, if you have a number that's bigger than 1, this value of n, not this value n, so your normal number. So like the distance from the Earth to the Sun. So anything that's bigger than 1 on large numbers, you're going to have a positive value of 10 because they're large numbers. So when you multiply by a power of 10, you're going to get bigger and bigger and bigger, adding those zeros on at the end. However, if it's smaller than 1, so any decimal values, you're going to have a negative power of 10. Okay, let's look at some examples. So we have 6 numbers here. We're going to put each of these numbers into scientific notation. So the first thing you want to do is you're going to put the decimal point after the first non-zero digit. So going from left to right, the first time I see something that's not 0 is a 3. So I'm going to say 3.578. Now I need to, so this is going to be 10 times 10 to some number. So to get that exponent, I'm going to say, okay, how many times did I move the decimal to get here? Well, it started here at the end. I had 1, 2, 3 to get to this spot. And this is a big number, so it's going to be a 10 to the power of 3. Okay, 984.35. Listen, it already has a decimal point, but that doesn't really matter in figuring out this first number. So again, I'm going to do the first one that's not 0. So in this case, it is 9. So I have 9.8435 times 10 to some power. To get that power, say how many times do I have to move the decimal place to get from here to here my answer. So I started here and I want to get in front of the or behind the 9. So I go 1, 2 times. And again, because this is a bigger number, is going to be a positive 2. Okay, looking for the first non-zero digit. Well, that's 0, 0, 0. Oh, the first one is 5. So that's going to be 5.8 times 10 to some power. So I need the decimal to go from here to after the 5. So it goes 1, 2, 3. But this time it's a small number, so it's going to be a negative 3. Okay, for D, we have 624.87. Again, it's going to be the first non-zero digit. So we have 6.2487 times 10 to some power. So you need to get from here to here, right after the 6. There goes 1, 2 spots. And it's a big number, so it's going to be a positive 2. Okay, for E, the first non-zero digit is a 3. So I do 3.005 times 10 to some number. So to get from here to after the 3, I go 1, 2, 3, 4. It's a small number, so it's going to be a negative 4. Okay, first non-zero digit is a 9, so I have 9.8180004 times 10 to some power. So this time I only had to move it once, and it is a large number, so it's just going to be a 1 here. Note, when you're changing something into scientific notation, do not round until you get to this part, and then you round to whatever they say to do. So if they said to round to the nearest, let's say 10th. Let's say we're looking at this F. This F. We want to round this one to the nearest 10th. We would find this one, and then we would round it to 9.8 times 10 to the first. Now, if you rounded it here, you'd have 98.2, and then you'd end up with 9.82, which is not the same thing as this answer. It's just something to think about. Okay, now this is a little bit easier way. Scientific notation into ordinary notation. So if the exponent is positive, you're multiplying by a positive power of 10. It's 10, 100, 1,000, and so on. You're going to move the decimal point to the right. You're going to add in zeros to fill in the empty gaps. Now, a lot of the times you can do this on your calculator, although for bigger numbers, if you try to do it, it's just going to give you the answer back in scientific notation. So it is important that you understand at least the theory of this. So it's positive it right. So if the exponent is negative, what do you think it's going to do? It's going to move it to the left. And again, you're going to add in zeros to any empty gaps. So let's do some practice. So we're going to convert each of these to from scientific and ordinary notation, and then we're going to go ahead and write its name in words. So 9 times 10 to the 7th, we're actually physically going to do 9 times 10 to the 7th. So you could put in your calculator, but you're not guaranteed to get anything. So what we're going to do is I'm going to put the number here. Right now, the decimal point is right here. I want to move it to the right 7 because this is positive. So I go 1, 2, 3, 4, 5, 6, 7. And I'm going to fill in all of these gaps with zeros. So if I add in commas, I have one here, one here. So this means it is 90 million. Okay, this next one, 1.1 times 10 to the third. So I start with 1.1. And I want to move it to the right 3 because it's positive. So I go 1, 2, 3. And I fill in the zeros. So now I have 1100. Or if you want to be particular, it is 1100. Okay. 2.3 times 10 to the negative third. Note this is a negative, which means we're going to move the decimal point to the left. So start with 2.3. And I move the decimal point to the left 3. 1, 2, 3. Fill in the gaps. So it becomes 0.0023. So this number is 23. So just like I said here, like 1100. So I said 11, and then I said whatever place value this last one is. Same thing here, 23, and whatever place value this 3 is. So it's 10, hundreds, thousands, 10,000s. So it's 23, 10,000s. No, we do have to have this hyphen here, otherwise it means 10 thousandths and not the 10,000ths spot. Okay, 4 times 10 to the negative 6. Again, it's negative, so we're going to go left. So we start with the 4. Decimal point is after it, so I'm going to go left 6. 1, 2, 3, 4, 5, 6. Fill in the zeros. So this is 4. See 10, 100, 1,000, 10,000, 100,000, million. So this would be 4 millionths. Okay, 1.23 times 10 to the 8th. We start with 1.23, and then move it to the right 8. 1, 2, 3, 4, 5, 6, 7, 8. Fill in the gaps here. And adding commas so I can see the number. Okay, so this would be 123 million. Okay. Then 2.34 times 10 to the negative 2. So this time we're going to go left 2. So we start with 2.34. We're going to go left just 2 this time. So we only have 1 0. So this is 10, 100, 1,000, 10,000 again. So this is 234 10,000s. Okay, so now let's look at some actual examples of scientific notation. So let's say we have so the number of different 8-character passwords that can be made with 26 letters and 10 numerals is approximately 2.8 trillion. So let's put 2.8 trillion into scientific notation. Now luckily we already have only one non-digit number in front of the decimal, so that one's good. Now to deal with this trillion. Now remember, trillion is just a power of 10. So we can say 2.8 times 10 to the trillion has 12 zeros. So it's 2.8 times 10 to the 12th. So anytime you see this, like one of these power of 10 words, you can always change it to times 10 to that power. So example 4, a large power plant generates 2.2 gigawatts of electrical power. So giga is a prefix that means billion. So what this means is 2.2 billion watts. They want us to put the 2.2 billion into scientific notation. Again, so we do 2.2 times 10 to the, so billion has 9 zeros, so it would be 2.2 times 10 to the 9th. Now you can do this whatever this number is. So even if it just said like 5 million, said 5 million, it's still going to be the same thing as, actually, it's not a good example. If you had like 62 million, you can write that 62 times 10 to the 6th. Now, this is technically not scientific notation, but we will be seeing this in some examples. So it's scientific notation-ish. And that's just an aside. Okay. So sometimes we want to change numbers to make it into something that might be a little bit more relatable. So example 5, there are approximately 2.2 million marriages in the United States in 2015. So to help us get a better idea what that means, we're going to express this quantity in marriages per hour. So when you see 2.2 million in the whole year of 2015, what is that going to be in marriages per hour? So essentially, this is just a unit analysis problem. So what we want is the marriages per hour. What we have is a number of marriages, which is 2.2 million marriages for 1 year. So start with 2.2 million. Now 2.2 million is going to be 10 to the 6th. We start with that one because that's what we have in our want list. So we start with marriages. Now we need to get rid of years and get up to hours. So we know that 1 year is 365 days. So years cancel. Now I have to get rid of days. So I know 1 day is 24 hours. So days cancel. Now I'm left with marriages per hour. So I do my multiplication. So I do 2 times 2 times 10 to the 6th. And then I'm going to divide by 365 and 24. And we get 251.14 marriages per hour. So 251 marriages across the United States were happening every hour. So it's a little bit easier to kind of wrap your head around than the 2.2 million. Okay, example 6. Americans spent approximately 277 billion on new automobiles in 2015. So we're going to express this amount in dollars per person using a population of 321 million people. Okay. So what we want here is the amount in dollars per person. What we have here is there's $277 billion spent, and we have a population of 321 million people. Okay. So if we want dollars per person, then we can just take our 277 billion. Now, billion is going to be 10 to the ninth. And we're going to divide that by the number of people, 321 million, which is 10 to the sixth. Now, if you're going to put this in your calculator all at once, make sure you put parentheses around the numerator and denominator, especially the denominator. Otherwise, it's going to divide by 321. It's going to take that answer and then multiply by 10 to the 6th instead of doing the multiplication here on the bottom before dividing. So if you put it in your calculator like this, so it'd be 2, parentheses 277 times 10. To get the exponent, you do the caret, 9, parenthesis, divided by, parenthesis 321 times 10, caret 6, parenthesis, and then equals. You end up getting $862.93 per person. Now, this one might not be quite as helpful because not everyone buys a new automobile every year. But if everyone paid, it would have to be like the 862. So sometimes changing units help, sometimes it doesn't really. Okay, example 7. The 2014 prison population in the United States was approximately 1.56 million. How many stadiums with a capacity of 60,000 would this population fill? So if we were going to take all the prison population and just stick them in stadiums, how many stadiums would be full? So what we want here is the number of stadiums. This is how many stadiums would this population fill? So what do we have? Well, we have the 2014 population of 1.56 billion, or million, sorry. And then we have the stadiums has a capacity of 60,000. So one stadium can hold 60,000 people. Okay, we want stadiums, so I want to make sure that that stadium's on the top. So I know one stadium is 60,000 people. So to cancel out the people, let's forgot to put that here. So 1.56 million people and one stadium, 60,000 people. I've used that one. So the only other one people is this one. So the 1.56 million, but I can't put million in the calculator like that. So for the power of 10, this would be 10 to the 6th people. Nothing on the bottom, so people cancel out. I'm left with just stadiums. So you 1.56 times 10 to the 6th and divide it by 60,000. You get an even 26 stadiums. Okay, example 8. Annual worldwide emissions of carbon dioxide were estimated to be 37 billion metric tons in 2015. Express this quantity in per capita terms, which is metric tons per person in the world. Assume a world population of 7.5 billion. Okay, so in this case, what we want quantity in per capita terms, which is metric tons per person. So we want metric tons per person. what we have is 37 billion metric tons. And we also have a world population of 7.5 billion people. Okay, tons per person. So we have a tons and person here describing the same thing. So we do 37 billion. So billion is times 10 to the 9th metric tons. Divided by 7.5, also billion, so it's times 10 to the 9th people. Remember, if you're going to put this in the calculator, make sure you put parentheses around the numerator and denominator. Also note that because both of these are billions, we could also just drop billion because they match. Like, remember, you can only drop this if every single one of your numbers has that unit. So because this is billion and this is billion are the only numbers I'm using here, this is the same thing as 37 divided by 7.5. You can see that's because this is times 10 to the 9th times 10 to the 9th. And in math, we have something multiplied to the top and the bottom, then you can cancel it out. So 37 divided by 7.5, which is approximately 4.93 metric tons per person. Now, if you can't remember that, that's okay. Just put the entire thing in, and you'll get the same answer. Okay, last example. The universe is estimated to be about 14 billion years old. What is its age in seconds? Okay, so what we want is seconds. What we have is 14 billion years. So right away, we know this is going to be a really, really big number. Okay, so we want seconds, which means in my analysis, we want to start with seconds. What are my seconds? I want to get bigger to years, so I know that there are 60 seconds in 1 minute. And now I need to cancel out minutes, so I know there are 60 minutes in 1 hour. So minutes are canceled, but now I got to get rid of hour. Well, I know there's 24 hours in 1 day. Hours cancel, and I still need to get bigger to years. So to cancel out days, I know there's 365 days in 1 year. And I only want seconds to my answer, so to cancel out the year, I put my 14 billion. So 14 billion is 14 times 10 to the 9th years. And everything's canceled except for seconds. So when you put all this in your calculator, it's going to be such a big number, your calculator is not going to say it. What it will give you is 4.4. Actually, it'll have 4.41504. And then if you have the TI-30X, you'll have a tiny little times 10 here. And then it'll say 17. Now what this means, if I'm just going to go ahead and round to the nearest tenth. So you have 4.4 times 10 to the 17th. So it's a whole lot of seconds. That's it for freebie.